How many people care anything about I/O? Wow, it's the same set of people all the time. What's going on here? All right, so let's jump in. So one of the first things that I did a long time ago in joining Nvidia was to start looking at ARM and what it is we could do at ARM. And at SC17, I led a panel basically asking the question, for the ARM software ecosystem, are we there yet? And some people said, yeah, we're there. And I said, not so much. And so Nvidia has been sort of ready and doing ARM for a very long time, but not in the HPC space. We thought it would be prudent and right to sort of wait until things were more ready. And I think now we're reaching the point where things are ready, but they need a little more of a nudge. For really, in the HPC space, they really need something that's going to give you great acceleration in addition to power efficiency. So we said, all right, let's see what we can do to make that possible. So we made an announcement, a very bold announcement at ISC19, and said, let's go make it possible to do ARM with NVIDIA GPUs. So even if I weren't at NVIDIA, I would be stunned to see how this company swarmed and said, let's go make that happen. Huge amounts of effort, huge amounts of focus and concentration on taking stuff that we had. We actually had done this before for Tegra for a long time, but doing it in the HPC ecosystem and actually making it so that it was usable took a lot of effort. So how would you measure that we're getting closer? So this is one of the ways that you can measure this, is like, if you want to do stuff and build stuff, how are things looking with respect to apps? Are those applications in containers? Do I span both HPC and maybe some deep learning? How many people care about deep learning? All right. And do you have different kinds of libraries and graphics and things that you would want to see? Maybe you saw the demo that John Stone had done with these very cool molecules and that kind of stuff. So he basically just took his stuff, updated a little bit to run with the latest version of CUDA, which is not ARM specific, and pretty much it just worked. And we've had a lot of experiences from people who sounded a lot like that. So among the operating systems that we have coming online for this is SUSE. So David Byte, I think, was still working over the weekend to sort of bring up a deep learning app and be able to talk about that and get that running on top of SUSE. He's very proud of it, so go ask him about it if you see him here. And we're doing this across a wide variety of different systems. So, you could ask, well, so why do you need a GPU? I thought the ARMs are pretty good already. They have these long, scalable vector instructions and so on. Aren't they good enough? And apparently, there's some applications where it's actually worthwhile doing something with the GPU. And these are some examples. Okay, these are speed-ups of, if you have a ThunderX2 and you also add in a Volta, and the vast majority of the work is happening on the Volta here. So what have been other people's reactions? What's another measure you would say is like, well, where are people using it? Are they using it here in the States? Are they using it in Europe? Are they using it in Japan and other places in Asia? And so we have some kind of fun quotes from different people. So Satoshi-san at Riken has been getting going with this, and we got some great initial results. A long-standing work at Oak Ridge. We have a whole bunch of different applications that have been run through there where they have some early systems and have been brought up and working there. And Simon McIntosh Smith, I met with him again this morning and said, so, what do you have to tell us about what it is that we should have done better for this release? And he kind of looked at his team and they said, we don't have anything to say. It was as good as possibly be expected for what it is that we had. Okay? So I think Simon is a charitable guy, but he's also pretty hard pushing, right? So it's not easy to get that kind of a score from him. All right. So another thing is you could look at so where are things in the overall ecosystem? So you could see that, there are some things that might be grayed out and that are still coming. And some of those things have to do with, for example, some of the limitations that are inherent in this generation that we hope and expect to be fixed in the next generation of ARM CPUs. I'll talk a little bit about that some more. So one of the things that we found is we want to be able to enable a broad set of people, and sometimes to do that, the best way is to do it yourself. this is very much a practice of Nvidia. Nvidia, you might call Nvidia a data center company. So if we're going to be a data center company, we need our own data center. So we have multiple data centers, which would be way high among the top few in the top 500 list. But they're very large, and we sort of get the experience doing that with this. So we're essentially designing a reference system, and one of the things that we're doing is that it overcomes, by having a switch, for example, a PCIe switch, it overcomes some of the limitations when you're trying to do the GPU to GPU communication that I'll reference in a couple slides here. But this is, again, something we're doing broadly across the whole industry. So here are a number of containers that we have working on this. And this is the one that you may have seen in Jensen's keynote. And we do have sort of TensorFlow working with this. And so one of the things that we have done is essentially to take those containers and now in this early stage, for people that have been wanting to develop with this, and SUSE included, David says, yeah, I want to get to this, but I haven't yet. To essentially take these and try them out yourselves on your own systems, and then compare the performance that you're getting versus what's happening in other data centers, to see if somebody's ahead, what are they doing right that other people can learn from, sort of take some notes on that if somebody notices that they're behind relative to others on the score, to be able to address some of those kinds of things. And so another thing that I've been helping to do is to gather, we could essentially say, get 42 for this particular test, right? And what meaning does that have for somebody? So what we're trying to do is essentially look ahead to say, what are the challenges beyond the way people have traditionally been thinking, like having lots of accelerating devices in a single box, and what are the implications of that for system design? And what are ultimately the implications of that for making sure that the OS is well tuned, etc. So we're working with that. And I want to call out here too, we've had great communication throughout the Linux community and support from SUSE in essentially looking ahead to what it is we need to do to be able to, for example, migrate data between the CPU and the GPU and make it so that that all just works. Okay, it's unified memory. So here's some sample numbers. So I could have run this back to 1 here, but I'm just focusing on 2 GPUs and 4 GPUs and a couple different nodes. And for these data sets, some of them scale very linearly and it looks very well. Some of them are pretty flat. And this has today to do with sort of the characteristics of how much data sharing that you're doing across these. Okay. But we have run UCX and MPI and Charm, and we hope that with the next generation of ARM CPUs that will overcome some of those limitations so that we can move forward better together. This is not an issue with our GPUs or the CUDA system, but rather with the enclosures that they're going with. So this is why we're doing sort of a reference design with this, as I was talking about. So now I'm going to switch gears for the folks that were interested in some of the I/O parts of things. So I would say that one of my favorite definitions of a supercomputer is something that takes a compute-bound problem and turns it into an I/O-bound problem. So people have been doing that for a while. That's kind of cool. I think it's time to even the score. I think it's time to sort of bump up the I/O. So there are certainly companies, Mellanox, others, that are certainly trying to boost the amount of I/O that you can get into the box through a NIC. But there's another thing that you also want to do, and that has to do with moving data around inside the box once you get it in there. So if you think about a case where now, on these thick nodes that we're developing, where you have lots of GPUs all running inside one single OS image, you can have one very complicated sort of mashup app that does simulation and data analytics and machine learning and deep learning and visualization all in the same memory and keeping it there as a very rich app. Or you may have sort of a workflow that spreads those across multiple containers. And fundamental to this, the thing you don't want to have the developers worry about is, so where and how is it that I place my data? And for all these different connections, like moving between GPUs, sort of a multi-GPU, or between nodes, multi-node, how is it that I manage all that? And essentially we're taking this collection of technologies that apply across different systems, that apply in different platform contexts, and bringing them all together under an umbrella. So many of these things are things that we've known and loved and had for a long time, like GPU Direct Peer-to-Peer, GPU Direct RDMA, and some new ones that are just emerging, like GPU direct storage that I'm talking about, that we've been doing in this space. So that for things like where you get a year-on-year improvement in nickel, we got over 30%, 1.3x improvement in nickel without changing any code, for just being able to improve the particular ways that we were managing the sharing of data. And there are other different kinds of things where when you need a new API, then we'll go and offer that for you. So for the GPU direct storage, I'll talk about that now. This is something where, how many people have ever used p-read or p-write, POSIX read or write? Okay, so for that, it's essentially using something similar to this. So the traditional problem here is that you're bringing in through NICs, maybe the NICs are capable of doing 100 gigabytes per second, but the only way to do that in today's Linux, this isn't SUSE's fault, by the way, is that you have to go and make a copy of it in system memory of the CPU. And then you got to come back down, but there's sort of a narrow pipe going in and out of the CPU. So you're losing sort of 2x of your potential by having to go through the CPU at all. And you're losing some of the extra time and management for managing your memory, for making the extra copies, you're adding latency. Things may not, even though these are bigger numbers, in fact, the numbers that you may see in practice for something like this could be 6 instead of 50. And the numbers that you may see for coming out of this could be maybe in the 40s or 50s or something like that. So we see some big ratios. So if we could actually cut out the middleman, still use that for control, but be able to bring that straight in, that would be better. And so you can then think in terms of having lots of storage with data sets that are way too big to fit in your memory that can then come straight into the NICs. And instead of having to always have to go through the CPU, if the GPU is a place where you're doing the computation anyway, do it on the GPU. Send the data straight there. Okay? This makes sense to everybody? All right. Some nodding heads. It's a good sign. So does this do any good? So let's take an example here of where we're looking at essentially 8 drives, which is what you can get in a standard DGX2. And if you run through, so bigger is better. If you run through the actual, this is just a very simple test, moving data back and forth, read and write. Then you look at the values you get here, there might be some place in the 30s. And even if you had it sitting in your page cache in memory, it'd still be slower. Whereas if you're doing it in GPU direct storage, you're doing better. And if you take into consideration how much better you could be doing by dividing that by how busy your CPU is, if you don't have to use the CPU to move it, then you get, this is now a log scale, you're getting sort of like 10x better performance in this case. Okay, so freeing your CPU up to do other stuff, maybe you don't need as rich or heavy of a CPU for that. So we took this is kind of an extreme case, but it's a real one. Oftentimes in transaction processing, you may bring in a whole bunch of data, but then between transactions that you do, the data might be in a different format and you have to do different things with it. And because of that, you might have to nuke all the buffers that you did and sort of format them, recreate them. And so you end up spending all this time to allocate your memory, to preload it into the memory buffer of the CPU, and then to clean up, when you didn't really need to do any of that because you could have just gone straight to the GPU. So the bottom lines here are time, this is latency, so smaller is better. The GPU direct storage ones are down here, and the difference between these cases, for those that know TPCH, this is scale factor 1K, which is about a terabyte, fits in your memory reasonably. This is 10 terabytes, not going to fit in your memory. You've got to be streaming it out. That's why there's such a difference. Okay, so I'll just look at a couple other examples. Really cool demo, if you want to go see it, about the Mars lander with this. So there's a common theme here where across these different things, this other one is, in this case, there was a supercomputer, Summit was used, and created all this data, and then you had to suck in huge amounts of data, 128 terabytes in this case, so that you could visualize it. And in this case, you're doing molecular dynamics, and you have different poses, if you will, from macromolecules as to positions they take over time. And if you want to figure out which ones of those are stable, you want to compare them every time step against every other time step. So that's an n-squared I/O problem with data sets that might be way too huge to fit in your memory again. So then that's a huge I/O bottleneck. In another case, earth scientists will often have to settle for dealing with data sets that are maybe 5 terabytes when they really want to work with a petabyte. And instead of being able to take days to bring this in. They want to be able to do it with hours with bigger ones or minutes with smaller ones. So I find it fascinating that a lot of the folks from the Pangeo community were like, yeah, do you use GPUs? No. And it's like, well, how would you like to speed up your I/O? Yeah, I/O is my whole thing. And then you say, well, how about we give you much faster I/O? And they're like, sure, we'll use the GPUs. Now how would you like to do data analytics? How would you like to be able to do some deep learning? How would you like to do some visualization all on the CPU? And they're like, this is great. This is exactly what we wanted. We never knew it, but this is what we want. So let's looking at the speedups. Here we got basically a 9-time speedup from taking things through the CPU to being able to do things directly on the GPU. Here we got a 3x speedup. John Stone, how many people know John Stone? Several people? Okay, he's like a superhero. He did a bunch of heroic programming and got pretty close with the CPU, but he had to use so much, he had to use 4 times as many threads, which is not what he wanted to do, in order, for example, to get something that was compatible between Linux and Windows, and that was just getting in his way. So he was just delighted to have simple, clean APIs, and that's kind of the story here is you don't have to become an expert in all your memory management and allocation. You don't have to be an expert in the best way to move data back and forth. Just do it the simple and obvious way, like using POSIX read and write. Okay? So, and this enabled in these areas to be able to sort of, instead of making a safe bet because your simulations and visualization and processing take so long, start to ask what if questions, right? We all like to do what if questions and be able to say, what would that look like if I did this? Okay, so some takeaways. If we look on the ARM side, a number of customers have told me today saying, we believe that the reason why things went so smoothly on the ARM front is because you had all the infrastructure and you had the maturity in place to make things just work, no surprises. And so that's sort of a credit to why we were able to pull that off in a short period of time and what people's expectations and experiences have been so far. Our take, I think, would be, and many others have told us this again, is that sort of, we think it's getting to be about time now in the HPC space to add GPUs in and to pair them up with whatever kind of CPU people choose. And SUSE is going to be right there supporting those as well. So whatever it is that we need to do to accelerate the data movement among the GPUs and for multiple GPUs and multiple nodes, those are the things we're doing, and we're calling that Magnum I/O. And essentially, whether it's in the States or in Europe, or a lot of people essentially want to exercise their choice of what it is that they want to do, what kind of systems they want to build, we essentially want to partner with and enable all of those. So we encourage you to help continue to contribute sort of what your requirements are and where you need to go with this so that we can keep working with you to deliver you the best value over time. Thank you so much.